Hi everyone, thanks for coming. This is Chenyang Zhong. I'm a third-year PhD student from Department of Statistics of Stanford University. The topic of my talk today is large deviation bounds for the Airy point process. First, let me introduce you to the concept of the Airy point process, which is a determinantal point process on the real line with Airy correlation kernel, which is given in this form. Here, ai of x is the Airy function, which has this integral form. Originally, the Airy point process arises as a limit of rescaled eigenvalue configuration of a Gaussian unitary ensemble, also known as GOE, near the spectral edge. So we recall that the equilibrium measure of GOE is a semicircle supported on -2 to 2, and we are focusing on eigenvalues that are close to 2. And let me give a bit of motivation for the study of the problem of large deviation bounds for the Airy point process. Recently, it is proposed in Cowen et al. That large deviation of the Airy point process can be used to study lower tail of the KPZ equation. So here is a background slide on the KPZ equation. KPZ equation is an idiopost equation which can be formally written in this form. So it is a stochastic PDE with the Kc, which is the space-time white noise. A rigorous way to define a solution to the KPZ equation is through Kohl-Hopf solution. So let's start from Z of Tx to be the solution of the stochastic heat equation. Here we note that the stochastic heat equation is a perturbation of the original heat equation, and here we set the initial condition to be the delta function. After taking a logarithm of z of t and x, we obtain the Kohl-Hopf solution of the KPZ equation with narrow wedge initial data. So the reason for the connection between the Airy point process and the KPZ equation is explained by the following theorem, which is a moment matching identity. So on the left-hand side, we have a multiplicative moment of the Airy point process, where AK are the ordered points of the Airy point process. And on the right-hand side, there is an exponential moment of the solution to the stochastic heat equation. We can also plug in Kohl-Hopf solution here. A non-rigorous derivation of large deviation of the Airy point process is proposed in Cowen et al. Using Coulomb-Gas argument. The argument is based on rescaling the LDP rate function of empirical measure of GOE near the spectral edge too. So based on this moment matching identity and the large deviation of the Airy point process, a derivation of lower tail of the KPZ equation is obtained in the same paper. However, a rigorous derivation of large deviation of the Airy point process remains an open problem. And in this work, we will derive the first rigorous large deviation bounds for the Airy point process. So let me introduce you to some basic setups in order to state the main result. First, we denote by A1 greater than A2 greater than etc. the ordered points of the Airy point process. And we are considering a rescaled Airy point process empirical measure given in this new K. We note that there are two terms. In the first term, the scaling of K to the -2/3 corresponds to the edge scaling of the GOE. And the second one is an equilibrium measure. So by subtracting it off, we can study large deviation. And we also remark that here K is a scaling parameter which will be set to infinity. So we also remark that we are actually studying the restriction of this empirical measure to a finite interval, say -R0 to R0 later. Okay, so now we can define the topology of our large deviation. So we first fix R0 greater than or equal to 1, and we let X to be the set of finite signed Borel measures mu on this interval, such that this measure is a positive measure. We also equip X with this distance. The distance is closely related to weak convergence on this finite interval minus R0 to R0. And we can also define the rate function. So let Z be the set of compactly supported finite signed Borel measures on the real line such that this measure is a positive measure. Then we can define this function I0, which is a combination of this logarithm term together with this integration from minus infinity to 0. After defining I0, we can define the rate function I1 to be the infimum of I0 of mu of tilde, where mu of tilde ranges from measures in Z such that it has total mass 0, and when restricting to this finite interval, we get mu. We remark that, as we have explained, this I0 comes from rescaling the large deviation rate function for the empirical measure of GOE near the spectral edge, and it has already been predicted by Corwin et al. So now with these preparations, we can state our main theorem. So it has three parts. The first part establishes an LDP lower bound of speed k squared when the rate I1 of mu. I1 of mu is what we have just defined. Also, we conjecture that this lower bound is tight. The second result is established an LDP upper bound with the same rate, with the same speed k squared and a rate I2 of mu. Here, I2 has a nice property that it is explicit, non-negative, and also for any closed set F that does not contain the zero measure, this infimum of I2 of mu is strictly positive. So these facts clarifies the fact that the correct speed for this large deviation problem is k squared. And we also have an exponential tightness result. So for this compact subset of xk of eta, we have if we first take limit of k to infinity and then take a limit eta to infinity, this quantity we are going to go to minus infinity. So the usefulness of exponential tightness lies in the fact that it allows us to approach LDP upper bound by a local LDP upper bound, which is considerably easier to establish. We also want to remark that a similar result can be shown for stochastic Airy operator h of beta with general beta with the same proof. Here, the stochastic Airy operator is a generalization of Airy point process. Airy point process is the beta equals 2 case. And this operator is a stochastic operator acting on a specific function space, and it roughly takes this form. Here, B denotes the Brownian motion. And now let me briefly say a few words about the challenges in the proof. So the first one is that we need to approximate the Airy point process using GOE up to exponentially small probability. So this approximation at the level of weak convergence has already been established. But the challenge is that we need to estimate the probability up to such precision that large deviation bounds can be transferred between these two objects. And a second challenge is that we need to overcome the long-range interaction between particles in both the Airy point process and GOE. So let me introduce you to the proof ideas. We are approaching the problem from two perspectives. The first one is the stochastic Airy operator and the associated diffusion given here. So the nice property for the diffusion is that we can use Markovian properties. And the second one is from random matrix theory, in particular for the beta ensemble, which also includes GOE. The nice thing about this part is that we have explicit formulas which helps us to get the correct rate function in the lower bound. And there are three steps in the proof. The first one is a priori tail estimates for the Airy point process. which is mainly based on diffusion. And the second part, as we have already explained, is approximate up to exponentially small probability. And there are two components. The first one is to prove exponential decay of eigenfunctions of both operators up to exponentially small probability. And the second one is to couple along eigenfunctions using a tool such as the KMT theorem. And the last part is to establish large deviation bounds for beta ensembles so that we can use step 2 to transfer it to large deviation bounds for the Airy point process. And for this part, we need to combine edge-related results for random matrix theory and a priori estimate from step 1 to show that particles which are far away from the edge will only impose a negligible effect. We also have an application of our estimates of the Airy point process to obtain improved quantitative estimates for lower tail of KPZ equation and the half-space KPZ equation. That's because we establish our result for general stochastic Airy operators. And so for KPZ equation, we can take a beta to be equal to 2. And for half-space KPZ equation, we can take beta to be equal to 1. And we presented the result here for the KPZ equation. And we get upper and lower bounds for this centered and scaled solution. So the main improvement is that we improve the previous exponent 3 minus delta here to 3, so that we can actually get the cubic exponent when the tail depth s is much less than t to the 2/3. And the second one is that we get the correct prefactor here, so that we can show that when s is much less than t to the 1/6, the tail behavior of gamma t is pretty close to the Tracy-Widom distribution. Finally, here is an archive link for my paper. Thank you.